Okay. So, yeah. All right. So, test tomorrow. 4x6 index cards. They are bigger than your average index cards. Fill them up with space, right? There's not too many equations that you guys really need to know at the end of the day, but put the concepts on there. I'm going to go over some like cookie cutter sentences for like interpretation of slope, interpretation of R squared, stuff like that. Those are the kind of things you want to put on there. If you're confused of like the difference between left skew and right skew, you might want to write that on there. Definitely put the equations down, some big concepts that you personally are not, super strong with, but there's more than enough space to basically get everything done. It's at 12 in the lecture hall. If you have SSD, just go straight to the testing center. I assume you guys got notified, right? Do you guys yeah, so a TA will stop by at some point, probably me, to answer any questions. Be there a bit early. The test is going to start at 12:05 exactly. We're going to have till 1. Pace yourself. If you wear a watch, keep track of time, and somehow we will have a digital clock up, but really you got to pace yourself. There's I think 13 questions. They're not only going to take the same amount of time, but you got to work fast, right? Do not leave anything blank. At the very least, you should always be able to write down an equation or some words. Give us a reason to give you partial credit. That's what I keep saying. Don't give us a reason to just write a 0. Give us a reason to give you points, right? There should always be something you can put down. But go fast, do the multiple choice, get that over with, then move on. Any general questions before we start? Yeah. No, you just cut out a piece of paper if you can't find 4x6. Yeah. Both. Yeah. There's gonna be some multiple choice, some fill in the blank, and then mostly short answer. So something like, does the correlation go between 0 and 1? You say false. But then there might be, what's the term for a data point that's far away in the x direction from other points? You write leverage point, stuff like that. And then there'll be, the short answer, which is going to be all the math. So yeah, any other questions before I start? Okay, I'm gonna give you back your quizzes and tests, quizzes and homeworks at the end. Okay. So I'm gonna start by talking about linear regression. Linear regression is an important concept. We're gonna be talking about it for basically the rest of the class. The equation, well, let me start. Everyone knows this equation, right? Y equals mx plus b. M is your slope, b is your y-intercept. In stats, we're different, so we write it a little differently. Y hat, do not forget the hat. If you don't put the hat over the y, you will lose a point. I'll explain why in a minute. B naught, we say, if there's a subscript 0, we say naught, N-O-U-G-H-T, plus B1x. In this case, this is our y-intercept. This is our slope. So we're just moving around. The reason it's not y equals is because we are predicting values. The hat means we're predicting things. All of statistics' point is to predict things. If we have our scatter plot, we have our line. This point is not a data point. That's a predicted value. So that's why it is y hat. If it's just a y, that means it's a straight up data point like that, because that's what we know. So if it's data we know, there's no hat. If it's a predicted value, there is a hat. Then you might ask, how do we construct this line? There are formulas for the slope and the y-intercept. So the formula for the slope is r, our correlation coefficient, times standard deviation of y over standard deviation of x. If you want to be a little clearer in notation, you can write like that. one thing to notice is the correlation directly influences the slope, right? So if the correlation's negative, because standard deviation is always positive. So if the correlation's negative, the slope of the line is negative. So we have this, and then we have equation for our intercept, which is y, the mean of y minus the slope times the mean of x. The reason that works is because on the regression line, there is always the point x bar comma y bar. There are three equivalent terms for regression. There is least squares regression. There is regression to the mean, which refers to what I just said, the point that x bar, y bar is always on there. And there's the line of best fit. These all mean the same thing. But it's important to know that all these terms are equivalent. I'll illustrate again what least squares mean. So before I do that, let's talk about what a residual is. A residual is, we usually call it E. It is y minus y hat. So this is a data point. This is the predicted value for the same x. So if the predicted value, so if the data is above the line, it's positive. If the data is below the line, it's negative. This on this graph can be represented by this red line. It is this distance from the point to the line. Now, least squares, remember when we did standard deviation, how the numerator xi minus x bar is squared? That literally turns this into a square for every single point. And what least squares means is we are trying to shrink the distance of these squares as much as possible to get the most accurate line. So that's why least squares regression is what we call it. And line of best fits just because, well, we're trying to fit the line to the, to the data as well as we can. Any questions so far? Okay. So these equations are pretty important. There's also the standard deviation of the residuals, which is the square root, the sum of the residuals squared over n minus 2. Not n minus 1. The reason is because we're talking about both x and y here. So we have two variables, so it's two what's called degrees of freedom. So it's n minus 2. So you add all you square each residual, add it all up, divide by n minus 2 square root. That's your standard deviation of the residuals. There are 4 conditions that you might need to verify before you do this regression. There's the quantitative variable condition. This just means what you think it means. Is our data quantitative? If it is not quantitative, it'd be kind of obvious. The only way to represent categorical data is by a contingency table. You can't ever make like a graph out of it. Next is what's called the straight enough condition. This is a condition that will basically be here for the entire course because we are only talking about linear regression in this class. We're not talking about logarithmic regression or quadratic regression or anything. It's always going to be linear regression. This means, is the scatter plot linear? And on a test, if you have to fill this out, all you got to say is, if you see something that looks like this, you just say, yeah, that has strong form, it's linear, And then no outliers. That's pretty self-explanatory. The first 3, you can see all these just by looking at the graph, right? If there's a point all the way like over here, that's an outlier. But if there's not, then you can keep going. These first 3 conditions are also the conditions to check correlation. This 4th condition is just for regression. That is called the equal variance assumption. It is also known as the does the plot thicken condition. You can use either of them on the test or any quiz. So this refers to the residual plot. So this is what it looks like. Usually the X bar is our Y variable, and here are residuals. So this middle point is 0. There are positive and negative residuals. We want our plot to look patternless and evenly spread out. So you want points basically equally above 0 and below 0, and it needs to look random. We call it patternless. If you have something that looks like this, that means we're not dealing with linear regression. If you have something that deals with this, that means every data point is above the line, which means you should probably just shift your line up. So this is good. These violate, I'm just going to call it the EVA. You can use either term on the test, but it specifically, you need to have a residual plot. Yeah.
All four of those conditions are regarding the plot.
The first three only have to do with the scatter plot. But like you technically don't know if the straight enough condition applies if you just look at residual plot. Because it could be a quadratic regression and you have quadratic data. So quantitative variable, if there is a scatter plot, you automatically know it's quantitative. So either of those work. No outliers, you can see that from either. Straight enough condition, you do need a scatter plot. Equal variance assumption, you need a residual plot. So you need both of these. You will be given both if you have to verify the condition. Any other questions? So like something you'd say, first of all, keep your writing short, right? You don't have enough time, you don't have that much time as is. You know, quantitative variable, you know, if it's talking about, let's say, weight, right? You know, grams is quantitative, something like that, period. Straight enough condition, the scatter plot is linear, period. No outliers. We can see there are no outliers. Equal variance assumption. The scatter plot, the residual plot is patternless and evenly spread above and below 0. Done, move on. Okay, that's all you gotta say. There's never too much explanation needed for this class. Okay. So we have our correlation, right? Which is a number, some people got this wrong in the quiz, between -1 and 1. Which measures the strength of the relationship between X and Y. That's what I was looking for in the quiz. Some people, a lot of people actually said correlation measures correlation, which I had to take points off for that. But this is, you know, something that it means. Then we have a thing called R squared, and we usually use the capital letter R. This is literally correlation squared. You have to square it in the decimal form though. So R is the square root of R squared, you know. Do not square root it in the percentage form. You have to convert it back to a decimal. R is always going to be greater than or equal to R squared. The only way they're equal is if they're both 0 or both 1 or -1. Well, not -1. If R is 0 or 1, R squared will also be 0 or 1, but it's basically correlation is always going to be bigger than R squared. A common question might be the interpretation of R squared. For people who are in office hours, I already wrote this down. This is something you want to put in your card. So I'm just going to say X% of the variability in, I'm going to say the response variable is accounted for by the model. Of course, based on the question, you're going to fill in whatever the R squared percentage is and whatever the response variable is. Remember last week when we were talking about how correlation is not the same thing as causation, right? R squared is somewhat of kind of a measurement of if there are lurking variables. If our R squared is low, let's say our R squared is 45%, right? That means 55% of the variability in the model is not accounted for. Sorry, the variability in the response is not accounted for by the model. So if more data is not accounted for by the model than the data that's in the model, that means there's other stuff going on here. Does that make sense? So 1 minus R squared is the variability. I'm just going to say in Y not accounted for by X. So, or sorry, by the model. So the higher the R squared, the better. If our R squared is low, like 30% or something, that means we basically just chose the wrong variables. You know, if our R squared is low, that means there's more going on here than what we realized. And there's probably other variables, lurking variables, or we just didn't choose a good explanatory variable, which could also very much be the case. Any questions so far? Yeah. No, so X is referring to just whatever the number R squared is. That's for the slope. That's for the slope. Yeah. Which I'm going to do next. Yeah.
What is R squared?
It is the fraction of the variability in the response value accounted for by the model. Yeah, so it's the definition of R squared. But if it says, if you got a question, interpret R squared, use this sentence format and just remember it for the rest of the class. One sentence, it's easy. It gets the job done. Anything else? There's a chair over there. So now I'm going to talk about the interpretation of slope. I'll just write a B1. For every 1 unit increase in X, there is a slope predicted increase or decrease in Y. You need to say the word predicted because we are predicting values. If you say for every one, for every 1 increase for every hour studied, every additional hour studied, your test score will go up by 10%. No, it won't. We're predicting it'll go up by 10%. But at the end of the day, we don't know. We're making an educated guess using math. So put the word predicted in there. Yeah. There. So that did not help. Remember to use context. Use the units the question gives you. Fill in the blank for whatever X and Y are for the question. You always need to fill it out in context. Any questions so far? Are there any homework questions you guys want me to go over from chapter 7? Did you guys do the homework? I hope you guys did the homework. It's good practice, even if it's not being graded, but it's always good practice just to do it. I'm gonna go over number 26. This has a bunch of numbers and you have to fill in the blanks using the regression equations. I'm gonna do 26D. So we don't know X bar. We don't know S of X. We are given Y bar is 18. SY is 4. And R is negative 0.6. We are also given the equation Y hat is 30 minus 2x. Can someone tell me what the slope and the intercept are from the equation? Yeah. Yep. Everyone see how we got that? Now we want to find X bar and S of X. This is basically back solving the equations for slope and intercept. So we have this. Now we plug in some values. This is -2. We know R is negative 0.6. S of Y is 4, and we're solving for S of X. So you can divide by negative 0.6 on both sides. I don't know what that is because I don't have a calculator. And then this becomes -2 S of X equals negative 2.4. Oh, so S of X is 4.8. Let's see how I did that. Okay. Any questions? All right. Now we need, so this fills this in. Now we want X bar. So we have to use the other equation. We know this is 30. Y bar is 18. Our slope is -2. Solving for this. So this is 30 equals 18 plus 2x bar. Subtract 18. 12 is equal to 2x bar. X bar is 6. And now we're done. Everyone see how I did that? Any questions on this? You know, understanding how to use these equations to do things like this is very important. Like number 25 and 26 in chapter 7 deal with this stuff. If you didn't do those, I definitely recommend going through them because it's good stuff to know for tomorrow. One important thing to know is how to interpret a specific type of table. So this, I'm going to use chapter 7, number 44, in case you want to look over this again. You're going to get this computer readout. This is something that's going to pop up on basically every test moving forward. It'll pop up on some quizzes. And knowing how to read these tables is really important. I'm going to try to draw it similar to how it is. It'll always say like response. In this case, it is home average attendance. It's talking about baseball games. Sometimes they'll say R. In this case, it says R squared is 21%. S is, see, this is a big standard deviation, 7,000. Then you'll see these two columns below it. Variable. You'll always see variable and coefficient. So You'll see a table like this. First question I have for you guys. What is the correlation? I will require a calculator. Yeah. It runs, sorry. So we have variable and coefficient. Variable, the names of the variables, coefficients are the number corresponding to it. So what is our correlation? Yeah. Yeah, so it's the square root of 0.21 because here's our r squared. Out of these variables, is intercept B0 or B1? Someone take a guess. B0, right? Our intercept, it'll always say intercept. Intercept is your y-intercept, right? Which means this is our slope. Now, can someone tell me the equation for the line, the regression line? Who wants to try it? Yeah. Home average attendance. I think that's what the abbreviation is. Yeah. Mm-hmm.
12,000.
Mm-hmm. Not times.
Plus 7.
9. Yeah. This would be the equation. You could say y hat is equal to that plus x, as long as you identify what x and y are. It's better to just write the variable and put the hat over the y. Yeah. I don't know. It's probably better to write in parentheses if it's a whole word. Well, runs is our actual x variable in this case. It's our explanatory. So you definitely do need to put the word runs there or x. But put the hat over the y. Please don't lose a point in the test because of that. Does everyone see how we got this? Can someone tell me in context the interpretation of r squared? Using that sentence template I gave you a few minutes ago. Can someone tell me the interpretation of r squared in context? Yeah. 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 21% of the variability in home average attendance is accounted for by the model, period, done, full credit. That's all it is. Similarly, could someone do that for the slope of this line? Using the other sentence format. Who wants to try? Yeah. Well, you got yourself a little confused. For every additional run, there is a predicted increase in home average attendance of 59.389 people. So for every additional run, we expect 59.3 more people to attend the game. Yeah. Yes. Yes. That was my next question. So r squared is 21%, right? So 21% of the variability is accounted for by the model. That means 79% isn't, which is a lot more. So is this a good model? No, because, think of it logically, right? Are the amount of home runs a baseball team hits the only thing that's going to affect if people show up to the game? No, weather, how well the team's doing, if there's any famous players, population of the area, right? Like all these things are probably better indicators, but runs is not that good. That's what we get by R squared. There's a lot of other lurking variables here. And our explanatory variable just wasn't a good choice, which is why our R squared is so low. Everyone see that? So these are the things you got to look out for when you have a question like this. And that's generally how something like this would go. Another thing could be like, if they score 10 runs, what do we predict the attendance to be? And then you just plug 10 in for X and you get a number. Yeah. This one? This is the regression line equation. Something like that. This one right here, right? Yeah, just the equation of the regression line. Any other questions about this one or about this stuff in general? Yeah.
Credit for interpretation.
Variability in home average attendance is accounted for by the model. Yeah. But you definitely have to put in what the Y is. And that's it. That's it. Just you do that, get your point, move on. Nothing too complicated. Any other questions about chapter 7? We're going to 8. Okay. Any other homework ones you guys want to go over? Is there any other ones I want to go over? Yeah. Okay. There's a bunch of stuff in chapter 8 that is not going to be on your test. On Dr. Faulkner's list of things to skip, like re-expression and ladder of powers and stuff. The big thing about chapter 8 are 4 key definitions or 5 key definitions and how to interpret it. First, before we go into the definitions, so we have a scatter plot. Let's say this is 0, this is, 50. If we try to predict a value of Y for any X between 0 and 50, so any X within this range of data, that's called interpolation. We are trying to predict something for within the data set we already know. So interpolation is going to be really accurate, right? If right here is 25, if we know, let's say right here is like 10. If we know 26 had a value of 10 and we say 25 has a value of like 9.5, we're probably gonna be pretty accurate, right? Because we have a lot of data for this region. But if we have a data over here that we're trying to predict, maybe it'll be pretty accurate because we're, if this is 60, because we're not too far outside the data. But the farther out we go, the less accurate our model will probably be and the less we can really rely on it. Anything over here is extrapolation. I'm sure you guys have all heard that word before. We want to use linear models for extrapolation, but we also realize we can't extrapolate too far. If we're trying to predict, I don't know, what the median salary will be in 100 years. Well, sure, we could, find a regression for salary increases over the past, let's say 100 years. We can probably predict with good accuracy what the average salary will be in 5 years, 10 years. But in 100 years, who knows? Maybe there'll be hyperinflation. Maybe we'll all be dead, We don't know. But so there's always a decent chunk of X values right after our data that we can extrapolate from. But we just have to recognize the farther out we go, the less accurate our predictions will probably be. Does that make sense, everyone? So we want to extrapolate, but we know that we can't extrapolate. The more we extrapolate, the less accurate our data will probably be. Because we'll need more new data to make sure, there's always a chance once we hit 60 for whatever it is, it goes like that. Or it goes like that. But we'd need to collect more data to know that. So that's just an important thing with statistics in general. Just the limits of our linear regression. Next, now we have 5 key definitions. These are things you definitely want to put in your flashcard. An outlier. We've used the term before. You've heard it before in your life. In this case, the actual textbook definition is any data point that stands away from the other data. And visually, we can always see that, something like this could be an outlier, something like this could be an outlier. It's a visual thing. Obviously, for box plots, we have the rule of the lower and upper fence are kind of a boundary for our outliers. Next, we have a leverage point. This is a data value far away in the X direction. It is only in the X direction. So in this picture is data point 1 an outlier. This is one. Is data point 1 a leverage point? Yeah, right? Is data point 2 a leverage point? Not really, right? It's kind of right there at the end of the data. Is it an outlier? Yeah. So leverage point is for the X. Residual point is for the Y. I'm just gonna same sentence, but replace X with Y. Your data point can be both at the same time. If it is either, there is a decent chance it's an outlier. Not necessarily, not always. I'll show you examples when not always, but in general, if it's a leverage point and or residual point, it's an outlier. But their leverage and residual are separate notions. Next, an influential point is a point that changes the slope of the regression when removed from the data. I'll show you examples in a minute. Any of the previous 3 things can be an influential point. They do not have to be. If they are any of the 3 previous things, there's a decent chance it's an influential point, not necessarily. They are all kinds of separate notions that overlap. And then the last one, we've already talked about it before, but just to write down the definition of lurking variable in case it's needed. A variable not explicitly in the model that affects the ways X and Y appear to be related. The example I gave last week, I think, was COVID, right? Anything about, human spending habits, human socialization, anything, if we're doing a study over the past, 20 years, COVID's a lurking variable there, right? It's going to be responsible for a big dip, 2020, 2021, whatever. That's a lurking variable. We're not saying it explicitly, but, well, we know it exists. and it's changing the way that X and Y affect each other. So these are the definitions. The best way to show you this is by using some examples. I'm going to do chapter 8, number 32. So here's our first one. I want everyone to just say out loud when I ask, is that point on the left a leverage point? It's definitely a leverage point. Yeah, it's definitely a leverage point. It's far in, it doesn't have to be to the right. You know, this, it could be far in the, you know, the left. This is definitely a leverage point. Is it a residual point? So the way to do residual point, you want to draw, like, either in your head or physically, draw like a line of where you think the regression would be without it, and then where you think it'd be with it. Based on that picture, I just showed it's an influential point, right? We'd think it changes the slope of the line. Now, focusing, you know, actually, I should draw some different color. Focusing on the blue line, is that point in a residual point? No, not really, right? Or maybe like a moderate residual, but it's not super high in the Y with this blue line. What's the fourth one? Is an outlier. Yeah, it's an outlier. So it's leverage, it's an outlier, moderate residual, and it's an influential point. You guys see how these concepts, you guys see what I mean so far? We're gonna do 3 more, but this is how it generally works. Is this a leverage point? This point on the right. Yeah, right? Is it an influential point? What do you guys think? Here's what I think. Like, just without that point, there's really no direction to this. It's kind of how they draw it in here. Without it, it's probably like that. But with it, I feel like it's kind of like that, right? So based on how I draw that, it's an influential point. Is it a residual point? Is it high residual? What do you guys think? You can say yes, no, or like moderate. The blue line. Yeah, I'd say it's like moderate residual. Somewhat high residual. Is it an outlier? Yeah, definitely. Influential point's kind of the most subjective. As you guys I can see the looks on your faces. Yeah, because remember, residual is y minus y hat, right? So if this residual is low, that means y and y hat are close. Yeah, I mean, depends. Yeah, like both of them are not that high residual. If you had a point like this one, this green one, that's without a doubt high residual, you know? So the next one is this a leverage point? No. Do you guys think it's influential before I draw it? So here's what the line without it would be, without a question, right? Probably it'd be slightly influential. But not if this point were like here, it probably wouldn't be an influential point because there's so much data, like almost in a perfect line, that wouldn't really affect it. But in that case, with the black dot, is it residual? Right? Yeah. So is an outlier? Yeah, they're basically all gonna be out, right? This last one is a little different. Is it a leverage point? Yeah. Is it influential? No. Because, I mean, maybe I draw a little more like that. You'd expect the point without it to be there, and you'd expect the line with it to basically be in the same place. So it is not influential. Is it high residual then? No, it's basically on the line, right? So the residual is really low. So it's an outlier. So it's an outlier, it's leverage, but it's not influential. And so it has low residual. Yeah. Mm-hmm. Yeah, so you have to draw the line in order to tell. There's no way without telling. There's no way of telling otherwise. Because residual point, by definition, you need your predicted value from the regression. Yeah.
One's considered. Can you give an example of Brian?
I mean, the definition of an outlier is a data point that's far away from the others. So a leverage point is far in the X. So sorry, it's getting dark in here. So a leverage point and or a residual point are basically always gonna be an outlier. There are other hands. Yeah.
Would that point, not an outlier?
Which one?
If you're going to-
All four of these I'd say are outliers. All four of these points. The bottom right one, that's not an influential point because it's basically on the line, right? Because they're all slightly separate notions, right? Leverage is far in the X, residual is far in the Y. Influential is if it changes the line. But like in this example, it's perfectly far enough in both the X and Y that it's still in the line, which can happen. Yeah. No, it's definitely leverage because it's far in the X. Yeah.
Is it in comparison to the regression in time? Because
No. So it's well, okay. Sorry, I shouldn't have said no. Leverage is compared to the data. Residual is compared to the line. Yeah. For residual, you need the line. For leverage, you don't. Any other questions about this? Something like this is a pretty good, test question to see if you understand the concept. So understanding this, do you guys want me to do, there's a question right before this of 4 more pictures. Do you want me to do that or no? What do you guys want? Do you want more practice with this stuff? Not getting much responses. I don't know. We got about 15 minutes before the quiz. Yes or no? I need people to say something. No? Okay. Yeah. And the area under a line? What do you mean?
like with like the variable allows it scores.
Oh, like on the quiz last week and stuff?
Yeah.
Oh, yeah, I can go over the quiz. I forgot about that. Let me options.